Alright, welcome back to the second part of the assembly tutorial for Snake in ARM64. First of all, we're gonna correct a few errors we did yesterday. So I'm gonna go here. Yeah, or not. 1 second. Let me make this bigger. So first of all, the tail pointer we had here, we get the tail pointer address in x1, and we're going to store what we want to store here is the coordinate address, and that is in register x20, not in register x0. So let me correct this here. I'm gonna get rid of this. And then there was this weird thing why I used x20. So x23 here is completely useless. We're gonna remove that, and I'm gonna remove this 23 here is gonna become a 20. And I think these are the only 23 registers. And then the, oh wait, here is, oh, 1 second. Yep, here's also a 20, so let's check if everything is still running. Everything seems to be fine, and then I think the 20 was a substitution error. We're just going to use x2 for that. So every x20 is going to become an x2, and that makes it cleaner. x13 not needed. What was that? Okay, we have here x13 is not needed. I think we had here x10, so we're gonna remove that one and use x10 immediately. x10 is not gonna change if we use the multiplication direct opcode here. So let's check it, and to be absolutely sure, let's also go back into the debugger and to the initialize Snake. Wherever it is, it's right here. LLDB Snake breakpoint set right here. Whoa, what? V9 X2, register read X2. Register read X2, yeah, we need to change it here as well, obviously. Okay, LLDB Snake. Set the breakpoint always twice. And now if we are here, register read X2, we have the Snake in X2. And if we find our loop here back, this should be right about here. So read x2, that's the Snake. Let's do the same we did yesterday, and we missed the 3 here, 15.7, so we are 1 part through the loop. I'm gonna do this one, 16.7, also fine. 17.7 and 18.7. That's okay, so let's run it one more time to see if we now have the right tail pointer. Register read x9, register read x1. This is the head. Register read x1. Store 9. Where's this x9 here? Head. Oh, we're not there yet. Store x9. Not quite sure where I am right now. Register read x1. This is tail. Register read x2. That is the Snake, and Snake is the same as coordinate buffer, so we are fine on that end. So let us check this to be absolutely sure. Nope. So we have this. Now we're gonna end this, and here we have the 4303. That's the beginning of the coordinate buffer. That's correct. All right. So now let's run it again, and let's now make absolutely sure with the head. Register read x2. So now we have the snake in x2. This is somewhere here. Now we should get in x1 the head. So let's also examine that. xb. And now we move 6 in x9. x20. There's still an x20. This has to be an x2. Okay. Make LLDB. Set the breakpoint. And now at this point in x9, we have snake plus 6. This time it's correct. It's we start at 0. We have a length of 4. We have 2 times 3, so we have 6, 0, 1, 2, 3, and the 6 coordinates for x and y. And this is now register read in x1. That will be stored in the head pointer. Oh, the table is moving. 32x, 32xb. And now when we execute it, we have here the head pointer. So this is fine. So these are the corrections we made from yesterday. And now we're gonna continue. Clear, everything's still running. So today we're gonna start making the snake move. So how are we gonna do that? We have our file from yesterday. I was hoping, is it this one? It's here. Okay, we have one over. So we're here. So now imagine we have these 4 coordinates, and it's set up like this. And how do we gonna move it to the right? Well, it's pretty simple. We're gonna add one element here, and then we're gonna remove this one. Then we're gonna add one again here without actually adding it, but we are replacing it, more to say. So we're gonna go here, we're gonna replace the empty space with the new character, and then we're gonna replace the tail with an empty space. If I could do this, I could actually do this. Let's go here, go one forward, replace with the pound, go to the beginning, replace with the thing, and now we have this. And if I do that repeatedly, we can see how the snake would move forward. So that's the goal, and then we have to see what we do when we reach the end. All right, so let's write this down. Initialize snake, we have the print playing field, and now we're going to do move snake and end move snake. And we're going to get into the swing of things by doing the boilerplate. STP, FP, LR, and SP minus 16, and you're not forgetting the pound. And how we're gonna move the stack pointer in the frame pointer. And now here we're gonna move the stack pointer in the frame pointer, LDP, FP, LR, and do the whole thing with resetting the stack. Okay, so maybe we write this here. So the first thing is get the head. Well, we need, what do we need? We need the coordinates, and I have my notes again so we can have the right registers, but we need the coordinates. We get them over the head pointer, so get the head pointer. That's number 1. 2, get the coordinates of head. Then we're gonna add direct. For now, we're gonna go only in plus x direction, and the rest is then pretty much the same. So add 1 to x plus 1 to x. Then we move the head pointer 1 forward. So add 2 to the head pointer. 5, store new coordinates in circular buffer. That's what we're gonna do. And once we have that, okay, add symbol to playing field. Right, that's the idea. And then once we have done that, we're gonna move the tail for. We're gonna erase the tail and move it forward. So we're gonna say get tail pointer, and then 8 chop the tail off. Let me make all of this comments here. So that's the plan. So the function has essentially, in good old Uncle Bob fashion, it does one thing. Get the head pointer, we update all the head coordinate, then we move forward and erase the playing field. And then we do the same thing for the tail, and then essentially it moves 1 tile over to the right. And then we're going to do that for up and down as well. But that's then the same. Okay, so now let me look at my notes so I get at least the right registers. So we're gonna get the address page x9. We're gonna get the snake add page. Then we add to x9 x10, and we get here the screen buffer page off. In 11, I'll get the coordinates, not this, add page off. At x12 is gonna get what? The head pointer. And x13, x9 is gonna get the tail pointer. Anything else? Yeah, we got in 14 the direction. Why not? 1 in x9, direction at page off. Let me check here my things. All is good. Okay, direction at page off. Okay, so the first thing is we get the head. Well, we had the head pointer. This is the no. Here we have the address of the head pointer. Now we want the address of where the head is pointing to. So we have to do, where do I do this here? In 17. It's okay. So LDR x17, this should be from x12. So this is now in 17 is now the address of the coordinate buffer, where, well, of the position of the address of the coordinates in the coordinate buffer. I should always, there's a comma missing. So let's do that. Okay, so just to be sure. And now what we get, we have the address. So now let's get the coordinates of the head. And we used here 1819. So load byte 18, x12 offset 0, and in 19 offset 1. But not 12 obviously, but 17. So 17 is the address of the cornerstone. Like I said, we're loading from the head pointer the address of the well, it's like a classic pointer, right? We get the address at the point from the pointer, and now we use the pointer and get the actual coordinates. So let's make here a comment. This is, well, do I so say the old? Yeah, let's say old x coordinate of head, and here we have the old y coordinate of head. All right, so now we're gonna move. For now, we're gonna move in x direction. Move in plus x direction. That means we're gonna add to V18 a 1. 1, and the y coordinate stays unchanged. So I have to check, okay. And the y coordinate stays unchanged. That's all fine. So what did we say? Get the coordinate of the head, add 1, add 2 to the head pointer. We can do that as well now. So whereas the head pointer is at 12, so we're gonna, do we need the old address? I don't think so. So we can just add, no, it's the other way around, x12 a 2. So this would be updating the head pointer. And now we have the new address. Well, 1 second. Now we updated, this is not correct. 12 is the address of the head, so x17, we're gonna do add 2 to x17, and now we're gonna store the address of x17 at x12. So now we have taken the pointer, moved it forward, and stored the new address in the head pointer. However, we have not yet updated the coordinates. So now we're gonna do the opposite of what we did here. We updated x, so we're gonna do store byte v18, which is now updated by 1 in the x direction in x17 offset 0, and gonna do the same thing with the y coordinate. Now let us check if we here still in, well, we cannot be in the core, because this comes later. Yeah, but I think we're more or less, we are good. So let's, to see something, let us add this to the playing field. Right? So let's add the pound sign, the symbol. And where do I have this here? In x1. So let's use x1 for the symbol. And we need somehow the width plus 1 in x0. Now plus 1. And now we have width plus 1. We need the y coordinate. What was the y coordinate? V19. So we're gonna multiply. Where do we store it? In x0. Okay. x0. Where's the width? Oh, width is this. So we use this, and we use x is x18. And then we add to that the y coordinate. Right? No. What? Whoa. Y coordinate was multiplied, and this will be added. So let us write this down, so not confuse me, with plus 1 times y plus x. That's what we're doing. And so multiplication is of with x0 with plus 1, x19 is the y coordinate, and then we're going to add the x here. Okay, and now we're going to store byte. Where's our symbol? We had it already, I think. Symbol in x1. So v1 in x0. Is that the thing? Store one x10. What the hell is x10? x10? x10, x10, x10. What is x10? x10 is screen buffer. Oh. What do I? We're going to store x1 in x10. But we need to add, at one point, we would need to add x0 to x10. I am not... I do this right about here. Okay, so this is the right way. Okay, W1 here, this is our symbol. X10 is the screen buffer right about here. And x0 is the offset we calculated right now. So let's on it. And nothing happened. Yep. Well, that's always the case if you don't call the function. So we initialize the snake, and we're going to branch label move snake, and now we're going to discover all the errors because we didn't tennis. No, we got one. We have the longer snake. All right, that's good. So now that we have updated that part, well, we should actually check maybe, or if we have here well, we can do that. Object dump minus the snake. Let's go to move snake, LLDB snake, set minus address, always twice. So now we can check here our X position. Now this was the head, where it was something with 3. This is our coordinate buffer, 18.7. And now we're gonna run move snake, 18.7, and there is no 19.7, which we need. So we are doing something wrong, or we are in move snake. Oh, I didn't. No. Okay, run it again. I wanted to next this, so let's next this. Why does he not jump over the function? Okay, break set minus a here. Continue. Now we're at print playing field. And now there we see we did everything right, actually, because 18.7 is here and now 19.7 is here as well. So we had the pointer, we took the pointer, we updated it, we took the coordinates, went forward and updated it. You can also check if we have this. Is this the head pointer? We see now this is 43B. So 430B, this is exactly this address, so the new head pointer is also stored correctly at this address. Okay, so far so good. But now we added the new head, but we have to remove the old head. So I'm gonna have the chop off tail part. I'll check one thing, 1 second. Okay, so we are in the chop off tail part now. Well, it's pretty much same spiel. We're gonna get the tail pointer. Do we have the tail pointer already? Maybe we could. Now we could take this down. but we're gonna load this. I think x17 is no longer needed. Oh, I should check. So that's where I'm not. Yeah, 17 is a good register because we're done with the head. We can also load in x17 now the tail. So now we have the tail in x17, and now we get the coordinates. So we can actually, if I could read that. Well, no, I wanted to jank that. X13. And now we're gonna paste this. And x17, and this is now not the head but the tail. So now we have, before we took the head, we updated the head, we took the coordinates, we updated the coordinates, moved forward, stored the new coordinates, and then placed them on the board. Now we have to do first erase the tail and then move the tail pointer forward. So we're gonna do this part, use the symbol and all of this. Pretty much all of this we're now gonna do here, except for symbol we're gonna use the empty space. So let me check if I also copied this all here. 1 second, empty space, x0, 0, 19, 18, x10, x0, yes. So let's check that. I can, emoti, I think I read emoti. Empty space. So we have 4, but I have no idea if we moved forward. So let's take this here for a moment and execute it a few times. And no, we didn't do that correctly. Oh yeah, well we were a little bit too early on the trigger here. Well, let's check one thing. Let's comment this out. Let's see if we have 5 pieces now. Now I'm gonna comment this back in, and now this part should disappear. So we are good, but we did not do that. We took the tail pointer and we erased the part on the playing field, but now we have to move the tail pointer 2 forward. So that is x13. So we have to do add x17, x17 2. So now the address in the coordinate buffer is added 2, but now we're going to store x17 in x13. Let me cross check. I did that before, so that's okay. So this should, well, obviously work, but now we have to test it by moving multiple times forward, and that works. Beautifully done. So let us just do one thing. I think I did this part here. Under the x17 stuff, yes. So just so we're on the same page. Okay, so now we can move the snake forward. Now let's do that a little bit, because so we're moving forward. We have a segmentation fault. That was too much movement forward. Oh, there's 2 things we have here. 25, let's up the buffer here a moment. Yeah. So the buffer is one thing. And now we are right at the edge. That's like spot on the money here. So we are on the cuff, and now let's go one more forward. And the snake disappears into the void. Okay. And now it did what so I was like, where is it? But here's now, it went forward and it erased the new line character, and then here the line was eradicated and we lost the line here, and the next line is right here in the screen buffer now. So that's where the modulo function comes in. Well, what up? It's me from the future. You have now reached the part in the video where we just made the snake move, went to the border of the playing field, and overrode the \n character so that we deleted the line here. I made a few mistakes there. I was struggling a little with the thing, and I thought about sorting this out in editing. Then I also had a camera failure, and during the x86 recording I figured out I could do something slightly different. So all these reasons together made me decide I'm going to record this short part and hopefully do a better job, at least a little bit. And then I give you back to my miserable self from 2 days ago. Okay. So in the part of the video, the obvious part that we want to do now is write a mod function. And I recreated everything so far, so let's talk about the mod function. So let's say, let me make this a little bigger. Let's say you have something like 8 divided by 10. Then you would get as a result, obviously, the question is always how often, I don't see the equal sign. Okay. The question is how often does the 10 fit in the 8? And the answer is obvious 0. And now you can ask, okay, but how close was it? So what's the remainder? And the remainder would be in this case 8. Is 8, right? So let's take another number. What is if you have 12 divided again by 10? Then the result is this time it fits 1, and the remainder is obviously 2. I will do another one. What is it? I don't do that. Whoa, 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 whoa. We don't do that. Let's say we have 22. So we added 10. We have 22 divided by 10. What's the result? Well, that's obvious 2, but the remainder is still 2. Oh. Do I have shift lock activated here? 1 second. So we see the errata video is working very well. So this is 2 and this is 2. Reminder is 2. Okay, so if you play around with this or you just know it, then you will figure out that A mod B is absolutely equivalent to A minus, well, we can take this here. So A, let's take this for example. So this would be, in this case, 12. Let's do an example first. 12 mod 10 is the same as 12 minus this one here, 1 times 10. Right, so this would be 12 minus 10, which is 2. And that's the remainder. And we can do this for the 22 here as well. So this would be 22 by 22 minus 2 times 10, and that would also give us 2. So in general, we can replace this 2 here with 22 divided by 10, but floored. So this would be floor, like this, and the same would be here. And you immediately see, 1 second, let me type this out. You immediately see that Without the floor function, the whole expression makes no sense, because otherwise this 10 would cancel with this 10, and you had 22 minus 22. And that's the general formula. So let me place this actually as a general, well, I don't place this, I have this, and this is the reminder. I always have this on the GitHub at the end. So the general formula looks like this. A mod B is the same as A minus A divided by B floored times B. And the way now I remember this to have a quick access is the formula doesn't make any sense if the floor function is not there, because the B would cancel each other out here, and we had A minus I, which is just 0. Okay, but one interesting thing about this is that this is somewhat closely related to the Archimedean property. So, and I remember when I learned about real numbers, my professor stood there and said, well, let me tell you about what the Archimedean property is. It's this one. It says for every epsilon, this is a contrived version of saying, can I make this a little bigger here as well? Yeah, that's a contrived version of saying, for every epsilon greater than 0, and for every real number A, and you should always read this as for every epsilon greater than 0, no matter how small it is, and for every real number, no matter how big it is, there will always exist a natural number, so that n times epsilon is greater than A, the real number. And what I was about to go into is like my professor back in the day said, well, imagine there is some place JWD, and I didn't know what JWD means, because JWD is Berlin slang and means ganz weit draußen. And that's like basically the Berlin way of saying it's upstate New York. And the analogy that he gave was like, imagine you have a ruler, and again, think about no matter how small the ruler is, and you place it, and I give you a number JWD, so somewhere a long distance away, and you have to have a small ruler. There will always be a number at one. If you take the ruler and place it consecutively after each other, there is a finite number n that you will be past that distance I gave you. And always with these quantum stuff, you have to think about it no matter how small the ruler is or the epsilon, and no matter how big the number is, the existence of that number is guaranteed. And that's an axiom. Well, it's here in English, it's called the Archimedean property. And I know it as the Archimedean axiom, but it's basically one of the things that the real numbers are based on. And the point here is also for real numbers that the number is always greater. You cannot, because a real number, we don't know exactly how it is in relation to the natural numbers at that stage. So you don't know, you cannot hit it exactly, but you know you find one n of a natural number that you will be over that distance. Okay, so now that I have my anecdote out of the way, if you look at whenever I find it here, if you look at this equation, well, I have it here better. Where is the mod function? Here, that's the mod relationship. That's actually very similar, right? But instead of asking, is there a number that we can go past the value, we are asking, we have a value, and how often can we place our ruler to get just in front of the number, so that when we take the ruler one more time, we would be over. And the result that we get is, if we have the number just before and the real number, we take the distance between them. That's the reminder of the mod function, right? So I thought that's interesting. That's like, I was just thinking about that. So that's the formula. And now arm64 does not have a mod function, but it pretty much has this this instruction. It's called multiply subtract. So the first thing we're gonna do now is write a modulo function. After all the talk, we're gonna go up here and I'm gonna write modulo function, and we're back into doing something. I'm gonna store fplr sp, and all I'm thinking about is don't forget the pound, and I'm not forgetting the pound. And I'm gonna move the stack pointer in the frame pointer, so this is the direction, and then we go do the opposite here, r fp and ldp fplr sp pound 16 and return. So for the function convention, what we're gonna do is we have the input value is x0 will be the value, and x1, or I should say this is the dividend, and this will be x1 will be the divisor. And in the first video I did everything with division and then just with multiplication and addition, multiplication then subtracting. I think we're gonna use the msub instruction right out of the box. It's just better, and that's what it's there for. So a lot of words and no meaning. Pretty much that's a quote from the same math prof. So I'm gonna comment everything out. I'm gonna comment everything out. I'll delete that. And we're gonna do something. I place an x0 in, let's take our value, let's take a 12 or something, and x1 gets a 10. We need somehow the move opcode here. And then we're gonna branch label to the modulo function. Modulo function is already defined. Wait. I can unfortunately not see it. Oh, that's the old one. This has to go. Sorry for that. So this has to go. Undefined symbols. Start. Yeah, cannot comment this out. So here we are now. We can use our clear screen function. Okay, we are still running, and now we're in the modulo function. So the thing is, now we're going to simply implement this formula. And we have in our x0 we have the a, and in x1 we have b. So the first thing we're going to do is this division, and we're going to use an unsigned division, and that's going to become important in a moment. Unsigned division from x0, and I don't right now. Let's take 2 here, x0, I can also close this here, x0 and x1. U division, so now we should have in x2 the division. So let's just check that to not, because with the ARM and x86 stuff, I'm getting here. We have 23, that's also good. The 23 here, we have to comment out. Did I run it? No, I didn't. And here we have a 1. 12 divided by 10 is 1. So that seems reasonable. So let me do one thing here. If we reverse it, we should get a 0. Right? So just that we know we do it in the right order. Okay. So now, as I said before, we're going to use the m sub instruction, and it's exactly what it says here. We're going to store our result in x0 because that's what the modular function returns, and then we're going to multiply these two values, a and b, so x1 and x2, x1 and x2, and what we are subtracting it from is a, which is also x0. So if everything is fine, this should work. Snake, echo, and we get a 1 back. M sub 2 and 1 x. Oh, I move x0 here, the x2 in. So let's see that. And we get a 2. What do we want to get? That's also, oh, we want to get a 2 because 12 divided by 10 is 1, remainder is 2. So let's take a 17 here. And that should also work. 17. And if we take 37, we have our mod function. So that's that, and that's one thing that's important but not the real issue. Because if you remember what we want to do and why we are interested in the mod function is because if we are at the end of the playing field, we want to wrap back to the beginning. And the problem with all of this is that the mod function, what we had here, is always 0 if it's a multiple by the divisor. So I had also written this down somewhere. Archimedes was done. So this is the issue. So every time we wrap from whatever point that is, we're going to go back to 0. However, the 0 for us is the border. We don't want to be on the border. We want to be at 1. So we have to add 1 to it. But if we want to add 1 at the end, we have to subtract it first. So we have to really shift it to the left, do the modular function, and then shift it back to the right. And to be clear what we are doing here, remember this here is 0, and this position here is 50, right? Because we have a width of 50. Well, it's not 50. Well, this is 49 because we have a width of 50 when we are going from 0 to 49. And this here is actually the 50th position. Let me restore our playing field, and as again, like where is my readme? I have it all here somewhere. So here I illustrated that. Maybe I do a better graph, but this is for now. This is the 49, and the inner field is height minus 2 and width minus 2. Width minus 2 because we have the left border and we have the right border. So that's the value that we want to mod by. And we don't want to do the following. We don't want to do mod from 0 to width minus 2, but what we really want to do is mod from 1 to width minus 1. So when we are inside. And that's that's the range that we want to have. And of course, width minus 2 minus 0 is still width minus 2, and width minus 1 minus 0 is width minus 2. So the value stays the same, but we are staying within the bounds of our playing field. And we can do that by what I already said. We are shifting it to the left, do our mod operation, and then we shift it to the right. And the reason we want to do it this way is because we want to store the coordinates in such a way that they are in relation to the inner field and not to the whole playing field. If you now would add an offset, which we might even do at the end to get a scoring board or something, now you would have to always shift. Would have to shift it to the top, do the mod operation, and then when you place it on the field, you have to account for the offset. So the reason is, for real practical purposes, we want to have the mod function within the range. And that's the function that we're going to write now. And that's gonna be modular function. Let's go right about here. And we are going to write modulo range. And end modulo range, and let me put this here to the top. And we're gonna store our frame pointer LR minus 16. Don't forget the pound. Move FP into SP. Do it right about here. And LDP FPLR, comma SP, and restore the stack pointer and return. Okay, so how do we do that? Well, we are going to do this formula. This is the shift to the left, and then we're going to mod it by the width. And after the modding operation, we're going to shift it back to the right and add our offset from the minimum, so plus A in this case. I have here the interval is A to B. And this is all fine and well. And now we come back to this case. This relation should also work for negative numbers. And I have here, I made an example, and that goes back to the Archimedean principle. If I have here, I am at 1, so here's the border, it's at 0, I'm at 1, now I'm at 0, I am on the border, so we want to go now loop all the way back, and then I go minus 1, and I want to go all the way back as well, right? So I made here the example for minus 1, and if we take this formula here, maybe I should, x minus a mod width, so the shifting operation, then we have 0 minus 1, this is minus 1, we have the division here, it's minus 1 divided by 50, to floor times 50. And the important point here is that this is sign preserving. So to go back to the ruler analogy, now we have a negative number, so now we are placing the ruler in the negative direction. And then we get a 50, so we have minus 1, add 50, and we end at 49. Yeah, so this formula works if you use the correct modular function. However, our modular function that we just defined uses unsigned division. And because we're using unsigned division here, we have our negative number, and we are still walking with the ruler in the wrong direction. And that creates a wrong offset. Additionally to that comes that we have an unsigned number, and this is written in 2 complement, and this will be then reinterpreted as unsigned binary number. So if you have minus 1, that's an insanely big number. It's 2 to the power of 64 minus 1. Right? And you can make this example. I did this here, and you can look at it. If you do the mass to the power of 64 minus 1 divided by 50, and you will get 50, just by the chance of how 50 to 2 to the power of 64 minus 1 turns out. And that's not what we want. We want this result. And in order to counter that, we're going to add the width. We're going to use what we did here. Every time I added here, I went from 12 to 22, and I could have gone to 32, right? I will have 3. All of this will change the result of the division, but it will not change the result of the remainder. So for the mod function, adding the divisor is an invariant. And that's what we are going to use. Why is this here? Can this turn away? Nope. We're going to use this formula here. X minus a, mod the width, and then add the width to it. So we have a positive number, and we are staying in range of where we want to be. Now this formula is only valid in this range, but since we are going in incremental steps, that's not a problem. Also, I had the idea at the beginning, what I did, weirdly, I simplified this by my nature, and then I calculated this property, and then did the mod function. Actually, that's counterproductive because we have here b minus 1, we have here b minus 1, and we calculate this property once, and then we use it twice. So we place this in a register, and then we use it twice. So that's the whole idea now, to get the modular range function to work. So, having said all of that, where are we? Modulo. Modulo range. So now we have a modulo range. What do? We have, let us write down the function stuff here. So x0 will have the value. x1 will have our lower bound, so our a, lower bound, and x2 will have the upper bound. And the first thing we're going to do is we are needing this a here at the end, or I just could maybe copy. Can I copy this formula here? Oh, that works. Okay, so we are needing this a twice. Or maybe no, it didn't. Doesn't matter. So let's store that a here in a register. This might change. So x1 has a. I'm gonna store a. And now we're gonna do these two calculations, b minus a and x minus a. So we're gonna sub b minus a, and we don't need b after that anymore. So we're gonna put this in x1. So this should give us x1, and then now x1 minus x2. Does it though? So let's move x1 into x0 and check that out. So we have here now somewhere modulo function. That's gonna change that to modulo range. Place our value is something 7 first, our lower bound will be 1, and our upper bound will be 50. So now we would expect that we get 49 and we get 213 modulo range, and that's why we checked, because then we probably have to do it this way, ARM and x86. Or is it 43? What? Oh, yeah. We are not doing that. We are taking the 2, x2, which is b, and subtract x1. And now we are having it exactly the other way around, don't we? So it was correct, but it was not correct. 44. So what do we have for values? This is still not correct. Oh yeah, this is all. This here has to be a 2. So now we are swimming. 207. And that's why you watch this. Let me delete that. Let me place this immediately. And now did we do something? Echo 49. Here we are. So 2 minus 1. So this is b minus 1. Let's comment this here now. B minus 1. And since we don't use b anymore, now we can place this. Whoop, what is this? Is that top? No, not here. Now we can place this in the b variable. So now we have calculated this part, b minus 1 and b minus a. And the next thing is we're going to calculate a sub of x minus a. So we're going to use x3 for now. We're going to use, whereas x is in x0. And, well, no, yeah, x0 here. We're going to use x0 and a is x1. We didn't overwrite x1. But now we have, so here we had x2 b minus 1, so we have to read it from here. So this is now x minus a, and we place this in our x value. So the x value is now gone, but we also want to call the modulo function. So now we're going to add this part here together. So x minus a plus x minus b. So we're going to take x0. Place it in x0, but we're going to take x0 and add it to b minus 1, which is x1. And now we're going to change this because we don't really need x2. We place this immediately in x1. So at this stage now we should have, can I go a little bit down here? No. Where is this? We should have this value in x0 and this value in x1, and we have backed up here a in x4. So now we can use our modulo function, label modulo function, and the result of this would be in x0. So let's just keep going. Let's assume it's there. So we want to take the result and add, in this case here, x4 to it. And that should give us the result of modulo range. Well, it did something. And we have 8. So this, where are we? 7. So now let's think about this. We have 7, but we added 1 because of the border. Let us check. This doesn't look correct. Wait. So let me check this. If I have it with a 1, I get a 2. I don't want to get a 2. Do I? So let us check that. Restore a, and we add a to the result of the mod function. That's correct. And I'm 1 second away from stepping through this. We subbed, and we added. Modulo function, that should be our result. Let's step through it. Let's take the address. And let's, oh yeah, we allow this. So let's check. We have x0, our value is register read x0 is 1. In x1 we have also a 1. Do we want this? Let's take something like a 7. Same spiel. Allow it. So here we are, register read x0, register read x1, we have now 7, and register read x2, our upper bound is the 50, which is a 32. Yes. So now we're gonna step into it, do our function prolog, and now we should have in x4 our a, which is see, that's where I went off the rails. We have our value in x0. So the function stuff should be like this. So let's run it, and now we have 7 and we get an 8. If we have a 7, we are counting. Well, let me. Do I want an 8? I don't think I want an 8. 1 second. If we have a 1, if I have a 0, well, I can say if I have a 0, I want a 1, right? If I have a 0, I want a 1 because I don't want to be in the border. And if I have, so this is correct. If I have a -1, I want to go all the way to the end. And -1 gives us a 2. That's definitely not correct. So that's definitely not correct. Good. So now we can check why. So let's step through it. Believe me, it's going better than last time. So we went through. We have this. Register read x4. There's nothing. Register read x4 should now have our a, which is 1. This is correct. So now we should have. I cannot read, unfortunately. Register read x. What's that? Register read. I want to have x1, which has a 1 now. This is step. Register read x1. Why does it? No, this is a 31 here, right? Yeah, that's a 31. Okay. Then it's fine. We have this, and let's check our x0 is still the -1. Now we're gonna subtract from -1 the value 31. Is this what we want here? This is wrong line. I think I see the error. Modulo range. Do we have anything here? So here we are. We are here, and this is supposed to be x minus a. So x0 minus x1, but I did change x1. So we need to be careful here. Let's take x3 here, and then x3 is b plus a, so we add x0 to x0 to x3 here. So I hope that's better. Minus 1, 1. This is still not right. So we are not doing what the formula says. We want b minus a in x3, and we want to keep that in the register. We have x0 minus x1, which is x minus a. We have this in x0 now, and then we add x0 to x3, which is this part, and we have it in x0. And we mod it, okay, we have nothing in x1, so we want to have in x1 the b minus a, which is x3. Minus 1, and now we are at 48. That looks correct, because with minus 2 is the 48. And let us go here and check a few more values. So by 0 we know we want to be at 1. So what do we have here? That's 49. 49, right? Now we have minus 1. This is the 48. We're moving backwards. That's beautiful. And if we have a value like 17, we won't still have the 17. Okay, so this looks correct. I'm not 100% sure I have the same registers because I didn't look at the notes now. But in essence, this is the same. So the final thing I'm going to do now is take these two functions and copy them in the video that you will now continue watching. So all I did is the modulo function. Oh, I want to say one last thing, and the modulo range function. You see, it's like we're calling here the modular function, and I will keep that for persistence, but we are here doing the whole stack prologue and the aftermath. So in reality, we should really comment this all out. For a leaf function, none of this is necessary, right? This will still work. And the same here. And then if we are honest, we have a function with two instructions, then we can also say, why even call it? Why not use udiff and msub right about here, right? But because this is a beginner's thing, we're gonna keep the prologue and everything in, and we have this one function call for now. We're like, everything is in flux a little bit. So I just wanted to have that mentioned, that I'm aware of it. That's the point. So now we're going to take all of this, modulo range, when I cannot see this right now. This is the modulo function, this is the modulo range, the new one. It's yanked. So I'm gonna open the snake function that we did last time, modulo function. Nope, modulo. And all of this. Now don't make a mistake here. This. this is too far. I think we should be here. So now we have, no, I don't trust this at all. Let me get this here again. Modulo function, modulo range, and modulo range. So, okay. And now we're gonna go here, modulo function, and modulo function, modulo range. And here you see how I calculated the -2a, and that's unnecessary. And we should be right about here. Okay. This should be fine. We have now this part. And now I'm gonna test if that compiles, and if it does, you will not hear from me again, but I give you back to my old miserable self. So let's check it one more time here. 48. So hopefully we're good. Let me check the camera 1 second. Freaking out at the moment. Oh, we are still recording. Sun is now getting a little cloudy. And we have hopefully the hardest part done with the modulo range function. And we need the modulo range function also because we want to store the correct coordinates in the buffer. Because if we don't do that, we always have to do the offset at the end, which is extremely more frustrating than dealing with this here once in the range function. I'm not gonna. Why is this here? Okay. Okay. Modulo range. Where were we? Move snake. That's the main task. So, where were we with the direction? Here's the direction heading. And here we have the head, the tail, chop off tail. Where do we move the head? X direction, all of this is happening here. And here is the board adding of the head. All right, so where are we adding? Uh, 15 modulo range, we need to do this now every time we add. And we need to do this a few times now. It's getting cold here. We need to do it for the buffer. For the buffer and for the coordinates. So let's do it for the width, the height, the tail, and the thing. Okay. So we add here, somewhere we added the one for the direction. Now at one position we're going to do that also for the y coordinate. So now we need to move. I have here, still have from this morning, a little bit of chocolate. As you see the moment, an Easter bunny from the x86 is camera failing, mod functions annoying me. Batteries going down. Okay. So what's the idea? We moved this, we need everything in the right registers for the calling convention, so we move x18 in x0 because that's the value, our new value. In x1 we need the lower bound, which is a 1, and in x2 we're gonna need our width minus 1. And then we're gonna call branch label modulo range. And then we get the result in x0, and we're gonna move it from x0 in x18. Okay. And then we're gonna do the same for y, but at the moment we don't need y, but we're gonna do the same here for the tail. Actually, no, because the tail will have the right. We are not adding something. We are only adding something here for the pointer somewhere here. Okay. So now we're going to do that. We have to do it for the y coordinate here, but let's first check it if it works for x. And now where's the buffer though? We are adding 2 here to the buffer. So here, we're going to do the same. We're going to move x17 in the value. Now we need in x1 the lower bound, which is the coordinate buffer. So it's pretty much x9, the snake. We didn't destroy it. And now I'm just going to use for the upper bound, instead of adding the coordinate buffer size, we're just using the head. This is 1, this is 2, this needs the head, and the head is x12. Oh, and now we have fear. We don't use x9 in the mod function. I don't think we use 10, 11, 12. So all of these registers should be fine. So we're gonna store. We have this, so we're gonna branch label modulo range, but we are definitely going in the debugger in a moment. And then we move it back from x0 into what? x17. And then we store the new buffer address. Well, yeah, all of this sounds reasonable as long as I'm not running it. So the same then here. We add 2, we move it in x0, we move in x1 the coordinates. I don't know if we have it still here. The coordinates should be in x11. x11, those are the coordinates, and now we're going to use the head as the end address again. x2 and the head is x12. And we're going to use 9 here. Snake and coordinates should be the same address. So let's do that. Branch label modulo range, and then move the x0 back into x17. Oh, we have everything commented out. So let's get this here back in. I think we can get rid of all of this. So let's No, I don't know if that was. So we're gonna do this, and one time we call it. So let's see. Well, something happened. Just not what we wanted. What the hell is this? Okay. That's definitely unexpected. Move in X direction. We add 1 here. We add 1 with -1. X. Oh, we add 1 here. Well, 1 second. This is not. We're not supposed to do that. So we might have just moved forward. Well, we're still moving forward and we're not crashing. I don't know how many we need to reach the end there. So let's make another 15. Oops. Oh, it looks good. Are we looping? Oh, we're looping. The mod function works apparently, at least for the X position. So now, okay. Okay, that's okay. That's an interesting part. Before we test the rest, because we have here the 50, let's try this also. Okay, that didn't work. So the buffer is not working yet. Do we have the head even here? So buffer label. Let's do one thing after the other. Am I in insert mode? Where am I? So let's do one thing after the other. We have the coordinates right, but we not right with the buffer. Here, when we add twice, we have 1x9. What is... So we should check all of these addresses. Actually, let's do that right now. Object dump the snake. And we're gonna take here one of these functions. It doesn't really matter. So we go in. Oh, I can't read that. We are modulo ranging here something. Register read x0. Now this is the coordinate, so I'm trying to jump over that. I didn't. We are in it. Okay, we need to add register read x0. Snake plus 18. Okay, that sounds reasonable. Register read x0. Register read x1. That's what we want. CLS. That's no. Oh, okay. Wait. Snake x9 is not the right coordinate. So let's. I have not added the part, so we end up at CLS. Yeah, that's right. So move snake, and now we go to x9. And this is now, we're gonna replace that with x11. This should be the coordinates. Is that here as well. So hopefully that does the trick. Right, make, how can it be up to date? Did he compile? Okay, we are here. So let's reduce the buffer again. That's the interesting part. Okay, that seems to have worked. So let me do it even a little more. Okay, that's looking pretty good. All right. A relief after this nonsense. And now we're going to write a very primitive. Now we're going to write a very primitive sleep function. And the reason for that, we can change that actually at the very end because it's going to go make the CPU go brr. But I think that's the easiest way to do it, especially at the beginning. So we're going to do it. I'm going to say sleep function. Let me check my camera. Yeah, he's still okay. Okay, he's still okay. We are on time, on target here. Stack fplr. Frame pointer sp -16. Move fp sp. And do this here. You can please leave us alone a little bit. LDP FPLR SP 16 red. Okay. So, how do we do the sleep function? We're just gonna go into a loop and make the CPU go brr. So we're gonna make, we take one register, I don't know which one, as it doesn't really matter. Let's take x1 and move in a value 0x the maximum value. And then we're gonna move keep x1 and we're going to put in the value speed. I'm going to define this here. EQ speed. And this is going to be the second part of the operation. So we're going to put, so we have the F, and now we adjust this a little bit here. I don't remember what is a good value. 0f. Well, let's do 0xf. 00ff maybe. For the beginning, I can check this. And now we go in x0 gets a 0. x0 gets a 0, yeah. x0 gets the value 0. And then we're gonna have sleep loop. I'm gonna compare x0 with x1 and branch equal to end sleep loop chuck and sleep loop, and otherwise we're gonna do, well, let's put here, oh well, we're gonna add 1 to x0, add x0 a 1, so we have something to do, and then we do a bunch of no ops like this, and at the end we branch back to the sleep loop. So that's CPU intensive, and there's a better way to do it with a deselect call. At the very end, I probably switch that out. The unknown fix-up kind. Move x1, yeah, because it's not x86, it's ARM. Okay, so let's test it right at the end here. Where is our stuff? We don't need this anymore. We can just delete this. Print playing field before we end sleep function. I think it's sleep function. So segmentation fault. How can we have a segmentation fault? We know why. We already know why. Well, that was the sig fault. Compare x1. That felt a little fast there. Branch sleep loop. Compare x0 to x1. Branch equal and sleep loop. Well, maybe it just felt fast. Where's the FF? Let's try this. Okay, that did something. So we have to adjust now. What value did I choose here? I have no idea. 0D. 0D. This is by pure, or we can leave FFF for now. Okay, so we move the snake, we print the playing field, we clear the skew, we initialize the movie, initialize the snake. This has also nothing to do. Now we make here a game loop. And now we're gonna say branch game loop. And that's not good. We have to clear the screen. And that's crawling along. Okay, we have something moving. So let's adjust the speed here. And check it out. We have something moving in one direction. All right. Okay, is the battery here fine? Oh, I changed that. That's all good. Is the battery here fine? Yeah, I don't know. Nobody sees it. So we have it moving. So the question is, what happens? Well, we didn't do that yet, right? Well, we can do one thing. We had our plus X position here, and we did the mod in X direction. So let's trust the process and put the 19 here, move x1 also, the offset is also 1, and in x2 we have height -1. And then with -1, height -1, branch label modulo range, and move x19 x0. So this should work in theory. Oh well. So let's not add 0, add 1 and turn off the x. And that works. So now the real secret is that if we can sub it. So in other words, can we move in the other direction? That was somehow sub 0 is still 0, no Mortal Kombat. So let's test this one. And that works as well. So this works. So let's try this as well for the y coordinate. Add here. Okay, so we have all the directions working. And all with a small buffer as well. So we are good on all ends here. So that was the move snake function. Now there's one thing I wanted to do. So now comes the magic. Not the magic, but the... So let's say... Well, remember, what we're doing right now is we're doing the following steps. We're doing a two-part process, but we print the snake one. We're going to the end of the snake, we append this, we go to the beginning and replace this. Right? That's how we move the snake forward. So I should use replace here, replace this, and replace this. Okay, but now let's say we're going down. Going down! So let's say we're going down here. Is this down? This is, I think this is down. So we're going down, and the snake would be, let's say, longer. Let's say instead of 4, it's 11. Well, that's okay, because we don't have a big enough buffer for that. So let's say it goes down. That works as well. However, there's one thing. If we do 12, this will also work, but now notice there's exactly one space in between. So it should work with 13 as well. Right? And then it goes, and now we have a disappearing act. That's the disappearing snake. How does this happen? Well, what's happening is, well, let's see that again. If you see it, it disappears slowly. So it goes around and then disappears. And the reason that's happening is the snake comes. Well, I can probably just do that. No. GV replace. Oh, hey. Replace this, and we have it here as well. Replace this. So this is our snake. And now, so this is our snake, and we have now explicit head right now, but the snake is here. So it will only move forward. Let's say for visualization, that's the head. So what it will do is we'll add a new head, place it here, and then delete the head at this position. And because we have a two-step process for one step, we are adding the new head where the old head would have been, and then move the head forward. But by moving it forward, we are erasing it. And that's not good. So what we have to do to fix that is the counterintuitive thing. But it feels better to add one piece and then remove it, add one piece and remove it. But we're going to do actually remove one piece and then add one. Remove one piece and then add one. And the way we do that is by reversing the process. So all of this is head stuff. At one point we add the direction. Well, we can just take this. Where's our head? We're gonna take the head part, the tail part. I wish I could see that. Take this away from here. and do it right at the beginning before we add the head. And now hopefully this works. Yes, it works. So let's take the add. So I just took the head, the chop of the hair part. This is the pointer adjustment, and this is the part where we actually chop the tail off. So this is, can I have something here? This is chop, chop, chop. And then here we store the part, and then here we go update head. That is now from here going on. Where are our directions? Add 2, add 119. If we are doing this here again, we can see it, and now it works in this direction. Let's test all 4 directions. We can also do this for fun. Diagonal. Well, why not run it? Let's see what happens with our diagonal snake. But we have the add part. We add 1 here, add 1 here, 0 here. So if that runs and we have it going down, and let's take the 13 back to a 4 or something so we can actually see what's going on. So we have that. Well, can I go back here? We have this. I wanted to have here a plus X. I have this comment, so this should actually help me. So let's go here, do a sub. And this moves the snake up. And now try the X direction for good measure. So we're not making any mistakes. So this works as well. So we have fixed that problem, and I showed the invisible snake mistake bug, whatever you want to call it. Okay. Where are we at? I think that's okay. We have this. Oh, we want to do one more thing. We want to make a good head. So we're going to have a head symbol, because this is, let's do a head symbol, and I don't know what we use there. The head symbol is going to be somewhere. I have it somewhere stored. 1 second here. Head symbol head is 0x40, and I called it symbol head, so let's roll with that. Symbol head is 0x40. So instead of replacing, updating the pointer, receiving the coordinates, going forward, and just placing the piece, before we do that, we place the whatever it's called, the head. We replace the pound symbol at the symbol, and then update it with a head. So in other words, a lot of saying, I can just show this. Now imagine we have, this is our snake, and we have here our head symbol. Where is it? Here. Now we're gonna replace this part with a pound, and then we're gonna place the new head here, so it updates. That's all I'm saying. So how do we do that? We are going to do that at what point? We chop the head off, we update the head. So here we update the x direction right at this point. So here we store the, now where do we store? 1 second. Here, after the update, we store the head right about here. This is W1, and now this one gonna make the symbol head. Yeah, so this is the update. And now we're gonna copy all of that and do the same thing right before we do the update. So here at this part, we're gonna update all the coordinates based on the direction. And here we're gonna do the symbol. So let's check that out. And there's our snake now has a head. Now, and if we want to be, let's do an add here. So, and if we want to be pedantic, we should also do that in the initialization. But now we have a head pointer or a head, and now if we play it and have the exact position, we can also have it in a way that you can see and react to it later. All right, so let's keep going a moment, because we have the direction and we have to update we have to get the direction, and based on the direction what the control function will set in the direction variable, we will set the direction what the snake goes in the move function. So where's our plus x direction? I should look for plus x, and it's right here. So here's our plus x plus y, adding or subtracting, doesn't matter. We can, okay, we could move this up here. However, we don't know if the modulo or the modulo range function destroys x8, v18 or 19, but we can check. I think we don't. Otherwise, we have to store it or push it on the stack. So let's try this. Is this here? Oh, there was something. Well, I don't know why it didn't do anything. Okay, that works. Add. That works. Are we running low on battery? Okay, no. So this works. So the mod and the mod range function do not destroy our registers, or maybe they do. Oh no, this is an 18. So let's go. Yeah, that works. So all we have to do really now is, we should really do a switch function, but we ain't. We're gonna use a simple else if part here. So we're gonna get our direction. Let me check what register we're gonna use here. Move snake, don't know. Move snake, modulo range. So we use the x13 direction. Okay, so wait. Let me check if I'm still freaking out. Oh, good. Okay, but I think we are also good for the day here. So let's do the one last thing. We have the direction in x14 here. The address of direction. So let's get in x13 the x14 here, and now we're gonna compare x13 with the value 1, and then we're gonna say we have move forward. Maybe in the aftermath we're gonna add a switch statement, but for now not. Move backwards, move up, and we're gonna say move down. So we're gonna compare x13 with 1. Is this 13? Didn't we do that? Okay. 14, compare 14. Move forward. What is 16? Oh. V16. I don't know what that is. That's we're gonna move here. If we move forward, we're gonna take our 18 and add a 1. If we're gonna move backwards, we're gonna subtract. Oh no, this is moving down. This is moving, adding, and this here is subtracting. 1 and always 1. And this is end direction. And once we have it, we're gonna say branch end direction. Let's do that. So we compare 13 with 1. Or we're gonna go here and say compare 13 with 1. With 1, we're gonna say branch not equal to move backwards. Words. No. Then we're gonna compare here. I don't know why I put this here. Let's put this here. Compare 13 with 1. If it's not equal, we check backwards. Now we're gonna compare x13 with 2, and then we're gonna move to the next up, and we're gonna go here, take the compare it with 3, and then if it's not, we move down, and here we should have exhausted everything. Now we're gonna choose the 4 and move to end direction. I'm too tired right now. So let's do this. We're gonna move, and if we now initialize the direction here, this is a 2, should be backwards in theory. That's a backwards. Now if we updated a 3, this should be an up. It's a down. So, where is direction? This is a 3, this is an add, this will be a sub, and this will be an add. So this is now up, and direction number 4 is down. Okay, so this is it for today, for this video. So we made the snake move, and we made it move in all directions. The next time we're gonna get the input so that we can control it. So we're gonna get the input key and control the snake in all directions. So I think I have a preview for that. And assembly snake video arm. No, is that the third part? Make and snake, and that will be the goal for the next video, to move the little snake around with the keyboard. But that's another video, and hopefully we get this all done over the Easter weekend. Again, happy Easter, and see you in the next one.